Continuing our discussion of integer partitions, recall that we had the numbers p of n, and these are the number of weakly decreasing sequences, lambda 1 all the way up to some lambda k, and these are all positive integers such that the sum of the parts of these lambda i's is equal to n. So we can compute these numbers for various n. So for n equals 1, there's 1, 2 partitions of 2, 3 of 3, 5 partitions of 4, 7, 11, 15, 22, and so on. So this is just a sequence that we can compute, and we saw that, well, we talked about there's no closed form for this. However, we did find a closed form for the generating function, capital P of x, which the definition is the sum n greater than or equal to 0 of p of n, x to the n. And the formula we derived last time is this is going to be an infinite product, say of m greater than or equal to 1, 1 over 1 minus x to the m. And our combinatorial interpretation of this is important. Here, we're thinking of 1 over 1 minus x to the m. Choosing a term out of this infinite sequence is the same thing as choosing how many parts are equal to m. So we're going to keep that in mind, and we're going to think about a refined way to understand these integer partitions. And the way we're going to come about that is by looking at a 2-parameter count, p of nk, and this is going to be the number of integer partitions of n, which we can denote with this notation, such that the length of lambda, the number of parts, is exactly equal to k. This is a refined way to count the number of integer partitions. So if we were going to count, for example, the number of integer partitions of 6, if we were going to enumerate them, there are 11 of these. We could do them lexicographically, so always start with the biggest number you can. 5 is the biggest number, and then 1. We could do a 4 and a 2, 4, 1, 1. We could do a 3 and a 3. We could do 3, 2, and then 1 left over, or we could do 3, 1, 1, 1. When we start with a 2, we want to take the biggest number possible next. Now we can't take a 4 because we need to write these in weakly decreasing order, and we've already written 4, 2. So there's no point in writing 2, 4. So the next biggest number is 2. So this is really the impediment to getting a nice recurrence for the number of partitions of n, is this idea that we kind of have to, we're restricted on what comes next by what came before. So we could do it this way. We could do 2, 1, 1, 1, 1, or we could do 1, 2, 3, 4, 5, 6. Okay? Now, if we want to take this number pkn, and we want to say, okay, well, there are 11 integer partitions of 6, and we want to say how many of those have exactly 3 parts, then what we could do is just sort of check off our list. This one does, this one does, and this one does, and we find this number is equal to 3. And what we want to do is think, okay, well, systematically, is there some way that we can think about these numbers? And the recurrence relation that we talked about in discussion that we came up with is a lovely recurrence. Pk of n is equal to p, well, we can think about these things. Either your last part is equal to 1, in which case you can just take that part away, or your last part is not 1, in which case you can take 1 away from every part. So let me write down what this is. The combinatorial proof is this is if lambda k equals 1, then delete it. So we've lost 1 from n and 1 part. And this needs to be the otherwise case. So else, in this case, lambda I is greater than or equal to 2 for all I. And so what we're going to do is we're going to replace lambda I with lambda I minus 1. That's going to give us an integer partition of n minus k, because there are k parts from which we lose 1 each, and we still have k parts remaining. So that's our combinatorial proof of this recurrence relation. That allows us to compute these numbers fairly quickly. And if we look at this example, we can see that P3 of 6 is equal to P2 of 5 plus P3 of, well, 6 of 3. So when we write down the elements that we had here, the parts that ended in 1, we had 4, 1, 1, and we had 3, 2, 1. And we can see that, yes, taking these last parts away, deleting that and deleting that gives us an integer partition of 5 with 2 parts. And taking 1 away, so the other thing that we had was 2, 2, 2, and we wanted to end up with partitions of 3 into 3 parts. And of course, there's one way to do this, which is just getting this partition. So that's a way that we can understand these PKNs. And now we say, well, can we get a generating function for these? So these have this nice recurrence. How does that really work here? Here, we're not interested in the number of partitions, but the size of the partition. And we want to ask ourselves, is that really different? So the answer is actually not at all. If we think about drawing the integer partition, so if we take a partition, for example, let's take something like 4, 3, 1. I can think of drawing this with boxes in a row, similar to our Lego construction that we had, 3, 1. So this is a way to graphically represent the partition 4, 3, 1. And once we have this paradigm, we can think about things we can do to this picture. One obvious thing we can do is we can look at the main diagonal and we can reflect it. Reflect the diagram across the main diagonal. When we do that, what is the integer partition that we end up with? Well, here, this is going to go vertically, 1, 2, 3. So this is going to be the 4 is going to be the height. 3 will be the height of this one, and 1 will be the height of this one. But now if we read the rows of it, we get a different partition, 3, 2, 2, 1. And this is what we know as conjugation. So this is the conjugate of an integer partition. If we start with lambda, the conjugation is often denoted with a prime. And now we can think about this partition into k parts has a nice graphical interpretation in this paradigm. Here I have a partition into 3 parts, right? Because that's giving me the height. What happens when I do this transpose? The height that I have here, which tells me that I have 3 parts, becomes the size of the biggest part. And so that's what's going to allow us to make a relationship between this amount, this PKN, and this generating function. So maybe we'll keep this board. So remember that we had this generating function for all partitions of n, which is P of, x, is equal to the product of m greater than or equal to 1 of 1 over 1 minus x to the m. And now this PKN, we want to think about, can we get a generating function for that? Well, this one, we have this recurrence relationship, but here we can think of these in a different way by this bijection of conjugation. It's an involution, right? So it's a bijection on partitions, and it changes this condition of k parts to the biggest part is equal to k. So this is the set. This is, by definition, the cardinality of the set of lambda is a partition of n such that the length of lambda is equal to k. And this is in bijection with the number of partitions lambda of n such that lambda 1 is equal to k. And this relationship between the length, which is the height in this picture, and the size of the largest part, which is the width in this picture, is exactly this operation of conjugation. So they're equinumerous. And now that we have this, we can reinterpret this formula here. So if I say pk of x, this is going to be the generating function for partitions now refined by k. So this is going to be pk of n, x to the n. If I think about what each of these terms means, so choosing an element from this infinite series is telling me how many parts of size m, I've now put a restriction on what m can be. So this is actually a nice thing that we can put onto a computer. This is the product from m equals 1 to k of 1 over 1 minus x to the m, which is now a finite product. And so this is something that we can actually compute with. And the fact that this is a finite product is sort of tied into the fact that we have this nice recurrence relation for it. We have a nice way to understand this, and we can kind of tie that in together. And now this formula here, we see the k is the same here, but then we have a k minus 1 here. That's going to allow us to get a recurrence relation on the level of generating functions if we want. So we can do a lot more generating function magic. But the point of this lesson, I suppose, is this idea of doing this graphical representation allows us to shift our paradigm in terms of partitions. And that's an incredibly powerful tool in the theory of partitions. There are lots of sets of partitions that are equinumerous. We can see a lot of it through the generating function, or if we can see it graphically, it gives us information about the generating functions.